signals have been passed on to the IQ modulators, which is again the work carried out by the baseband processor itself. And these digital signals have been the bits have been mapped into the INQ symbols and is passed on to the digital to analog converter. Then the analog signal from the digital to analog converter have been passed on to the local oscillator and the mixer stage, in which the digital signal have been passed on to the RF stage. And in the RF stage, a power amplifier is employed in order to transmit the signal into a radio channel, in which where in the radio channel even the noise gets added to the transmitted signal. At the receiver side, we have a receiver antenna which receives the transmitted signal, and the receiver, since the signal gets affected with the noise, we also have a low noise amplifier with the automatic gain control in order to receive a roughly constant signal. And the received signal is passed on to a analog to digital converter, in which the received analog signal is converted back to the digital and is again down converted with the help of a digital down converter, and is again, and the INQ signals have been extracted back and is passed on to the baseband processor in order to perform the digital signal processing task. Now let's look at like what are the some of the applications in which a software defined radio can be made used. Some of the application areas in which software defined radios are used are the software defined radios are very much flexible when it comes to bandwidth requirements. So this flexibility has enabled some of the most widely used applications such as cellular base stations. There are a lot many open source communities which has hosted some of the softwares such as OpenBTS, which provide support for 2G emulation, and SRSLTE, which provide 4G emulation, and Eurocom OAI, which provide 4G as well as 5G emulation, and OpenLTE and Amerisoft LTE, which provide 4G and 5G emulation. With the help of software-defined radio, it is also able to have a protocol stack emulation in order to implement the 2G GSM standard, 3G WCDMA standard, and also we can implement the LTE protocol stack as well as the 5G setup. Software-defined radios also find a good pick, like when it comes to the applications such as wireless security research, spectrum monitoring, waveform prototyping, radio astronomy, drone communication, or aircraft navigation. And also it is very much widely used when it comes to wireless test beds. The software-defined radios are also majorly used in some of the radio communication techniques such as adaptive radio as well as cognitive radio, and also in the satellite communication and public safety radios. We'll look at the most popularly used and most well-known SDR hardware which is out in the market. The hardware which is called as Universal Software Radio Peripheral, which is USRP, has been developed by Matt Etes, who is the founder of Etes Research. Like Etes Research has developed USRPs in four families, like such as the B series families, which is bus series families, which gets interfaced with the host-based PC with the help of a high-speed USB 3.0 connection. Next, we have an embedded series USRPs, which gets interfaced with the host PC with embedded series USRPs, which can be operated as a standalone setup. And then we have a network series USRP, which can be operated either as a standalone setup or also on a network-based setup. Then also we have an X series USRP which has been developed by Etes Research, and these USRPs are used in for high-speed high-speed applications. When it comes to the USRP-based SDR system, the typical setup looks like this. So we will be having a host computer, which runs an operating system such as Linux, and and a USRP motherboard and a USRP daughter board. The daughter board which gets supported for the motherboard. Example here, the image represents a USRP X310 with the two daughter boards, and The host-based computer, host-based machine also runs a host-based software such as GNE radio, and this host-based software communicates to the USRP hardware with the help of a UHD, which is called as USRP hardware driver. And this software communicates with the USRP hardware, and the USRP hardware performs all the signal processing tasks with the help of an FPGA present on the USRP. And the INK signals have been transmitted and exchanged between the RF data boards. Uh, and the RF data boards converts the digital signals to analog signal with the help of analog and digital converters, and the transmission receptions happens with the help of the RF data boards. So let's look at what is the key difference between the USRPs. USRP, even though it is research was has been overtaken by national instruments, the USRP which is available in the market is available in two variants. Like one is the ATES based USRPs, and another one is the national instruments based USRP. The key difference here is that the USRPs which has been produced by the national instruments supports is most widely used with the software such as LabVIEW. So and the NI USRPs make use of NI USRP hardware driver, and these USRPs also support some other software such as MATLAB, and this MATLAB also make use of the USRP hardware driver, which has been implemented by the MATLAB. So and the technical support for this national instrument based USRP is provided by the national instruments itself. So when it comes to ATES based USRPs, the technical support is provided by most widely available open source communities. This ATES-based USRPs interface to the host-based machines with the help of a high-speed interface, with the help of a UHD USRP driver, and these USRPs run open source softwares such as GNE Radio, UHD, C++, as well as Python. Another flexibility of these ATES-based USRPs is that they give the flexibility in order to have a RF node development, which is also abbreviated as radio frequency network on chip development, where in which hardware description languages such as Verilog or VHDL can be made use in order to have FPGA processing on the USRPs. Now let's look at some of the software support that is available for the USRP. As we can see here, these are the most widely supported softwares for the USRP. When it comes to LabVIEW is most widely used for the national instrument based USRPs, and MATLAB is also the same. It is most widely used in the national NI based USRPs, and also it can be used with the ATES based USRPs also. Then we have OpenBTS software, which is again an open source software, which provides 2G emulation. Then we have SRS-LTE, which is again an open source software, which provides 4G emulation. Then we have OpenAir interface, which also provide 4G as well as 5G emulation. Then we have a GNE radio, which is most widely used software, and this GNE radio also has the ability to have C and C++ and Python capabilities. Then we have RF support for the ATES-based USRPs. So these are the, and the Xilinx Vivado, it can be used along with the RF in order to have the FPGA development. So these are the software ecosystems that are available for the USRP-based SDR systems. So let's look at one such open source tool, which is called as GNE Radio. And this GNE Radio is the most widely used open source toolkit in order to have signal processing task with the help of a USRP or a software-defined radio device. The advantage of using this GNE Radio is that the GNE Radio also gives the ability in order to custom develop some of the OT out of tree modules or custom made digital signal processing algorithms with the help of C++ or C programming or Python programming, which are the popular programming languages. Then this GNA radio can also be interfaced with some of the other software-defined radios such as HackRF, Lime SDR, RTL SDR, as well as USRP. And this software can also be used without a hardware in a simulation-like environment. The GNA radio software also comes equipped with most of the signal processing blocks which are already been pre-built and has been given as a library package. Some of the blocks that are already available are such as demodulators, vocoders, decoders, filters, synchronization elements, equalizers, etc. So let's look at like an example like how we can make use of a GNA radio in order to have some of the open source development. We'll go through. So here like we are making use of a GNA radio in order to implement a frequency modulation. Like here we are making a transceiver system such that like we are using two USRPs and we are transmitting from one USRP and receiving at another USRP at certain distance. So here we are like at the GNA radio in order to have the frequency modulation transmitter and receiver capability. GNA radio itself implements two blocks called as WBFM transmit for the transmitter section and WBFM receive for the receiver section. Uh, this WBFM transmit also contains some of the parameters such as audio rate, quadrature rate, TAU, max deviation, pre-emphasis, high corner frequencies. These are the parameters which gives the user a flexibility to have to make changes or to have the control too. So the audio rate defines the rate at which the audio is being taken for transmission, and quadrature rate defines the rate the rate which is the rate that is coming out of the transmit block. When it comes to the receiver, the quadrature rate is the rate of the input complex signal, and audio decimation is the decimation factor for the quadrature rate, and the WBFM receive will output the audio samples. So this is an example in which we are transmitting a 48 kilohertz audio wave or audio sample with the help of a WBFM transmit block using a USRP. So in this like here, as you can see, we have made use wave file source which takes the audio file and the audio file extension is .wab, and this audio file has been the quality or the amplitude of the audio is implemented a little has increased a little higher with the help of a multiply constant block. Then this audio signal is passed on to the WBFM transmit and is transmitted using a USRP. As you can see in this spectrogram, we have a signal. We have the audio extending up to 17 kilohertz. So like as you can see here, this part of the audio has more of the like frequency of interest, and when it comes to the edges of the spectrum, the number of frequency components are not much valuable because it contains less number of information and some of the distorted noise. So in order to eliminate these unwanted frequency components, we are like a GNA radio also gives the ability in which we can develop, in which we can implement filters or design filters. So like a GNA radio also comes equipped with a digital filter design tool in which like a filter can be an FIR or IR filters can be developed. So for the audio that we are transmitting, we have divided the frequency spectrum from 20 hertz to 17 kilohertz into 4 sections, and we developed a bandpass filters using the GNA radius filter design tool, digital filter design tool. So as you can see, the audio that we are taken, the input audio is divided into 4 sections. Like the first section is for 20 hertz to 6 kilohertz. Then we have 6 kilohertz to 10 kilohertz. Then we have 10 kilohertz to 14 kilohertz, and again from 14 to 17 kilohertz. So these are the 4 sections we have divided in order to identify the unwanted frequency components that is present in the audio that is being transmitted. So like this is the filter design tool that is available in the GNE radio itself. So like we can generate the filter coefficients, and we can make use of these filter coefficients. So as we can see here, we have generated four different bandpass filters for the different frequency ranges from 20 hertz to 6 kilohertz, again 6 to 10, 10 to 14, and 14 to 17 kilohertz range. And these filters have been made is in order to identify the unwanted frequency components. As you can see, the response of these filters, as illustrated is in the image. The first response is for the FIR bandpass filter from 20 Hz to 6 kilohertz. As we can see here, the number of the important frequency components are present in this frequency range itself. Then we went for the second range, which is 6 kilohertz to 10 kilohertz, and here even this part also includes some good frequency components at this section. So and then we went for the third frequency range. In this third frequency range also there are some frequency components that are present over here. But in the fourth section, that is from 14 kilohertz to 17 kilohertz range, we can see here like some of the frequency components are not much predominant over here. So like it's okay to be like uh, left it out, because like after listening to the audio there was nothing audible over in this frequency range. So the like once we have like identify the number of key frequency components, it becomes easy for us to have bandwidth requirements to be restricted. So once after the audio being transmitted, then at the receiver side, we are using a WBFM receiver in order to receive the signal. So here we are making use of a USRP source in order to receive the signal. And this USRP source here, what we are trying to show is that like we are making use of a bandpass filter which is available from the GNA radio itself, and a decimating FR filter in which the filter coefficients are designed using the GNA radius filter design tool. And the signals have been passed on to a WBFM receive, and the signals have been passed on to WBFM receive in order to receive the frequency modulated signals. And these signals have been passed on to the wave file and has been stored onto the wave file, as we can see here. Now that like the bandpass filter we are having, the response of the bandpass filter looks somewhat like this. We have a switch here. The selector acts as a switch, like which selects the response of the bandpass filter or the decimating FR filter. When the switch is 0, the response of bandpass filter will be selected and this will be output to the speakers. When the switch is 1, the response of the decimating FIR filter will be selected, and the response will be output to the speakers. So as we can see here, the response of the bandpass filter corresponds to switch 0. Here we can see the number of frequencies components that is received is quite lower, because of the noise factor also coming. As you can see here, it's quite lower. Then when it comes to decimating bandpass filter, when we made use of the filter design tool, the frequency components and the filtering has worked pretty good over here, and we can look at on the spectrum, it's quite visible. And then once we have the response, we can check on the audio quality that what we have received. So this is the response of the first response we use just only by using the bandpass filter. Ma'am, was it audible?
Yes, sir. Audible, sir.
Okay. So this
Sir,
is
I'm not
the
getting sound from this one, sir.
yeah, this haven't played yet. Yeah, this
Yes,
is the
yes.
response of the FIR filter.
No, sir. No, sir.
Sir, did you hear, sir? Was it audible?
No, no, sir, no, sir.
Okay. Once again, I'll play from first. The response for the band pass filter. Sir, now, sir.
No, sir.
Once again.
हेलो।
हाँ मैडम, yeah, I'm just checking this audio
ओके,
settings.
ठीक है, ठीक है।
Sir. Sir, now I'm playing the Sir, am I audible, sir?
Yes, sir.
Sir, now I'm playing the response of the band pass filter. So, so this was the response for the band pass filter. Now I'll play the response for the FR decimatic filter. Sir, yeah, was it audible, sir? Okay, thank you. So, yeah, this was the response. When we have the when we had the filter comparison for the WBFM receiver block for the FM receiver section. So, now let's look at some of the add-ons or the plugins that is available for the GNU Radio tool. Some of the add-ons or the plugins that are most widely or popularly used or are as listed here. The one which is called as GRADSB And these are the add-ons which are developed by the open source communities, and either by as a OOT module or out of tree modules. And these OOT modules have been developed using programming languages such as C++ or Python. And some of the plugins are GRADSP, and this GRADSP is a module which decodes the ADSP signals from the aircraft. Then we have a GRDSD, which is another OOT module which is developed in order to demodulate some of the digital communication protocols found on the handheld walkie-talkies. And this GRDSD will decode some of the protocols such as DMR, P25, NXDN, and X2TBA, and few others. Then we have GR Phosphor. This GR Phosphor is also a OT module which makes use of OpenGL or OpenCL acceleration in order to have a real-time spectrum visualization on the host PC. Then we have GR Inspector, and this GR Inspector is also a OT module which is realized in order to have signal analysis capabilities. Then also we have GRMRI, which is a software package which is most widely used for the biomedical signal processing or image processing applications. And GRMRI makes like uses software defined radio for magnetic resonance imaging. And there are a few others plugins available. So now let's look at some an example of one of this plugin which can be made used with a GNU radio. One such plugin example that we have taken here is GRADSP. This GRADSP is the OT module which decodes the ADSP signal from the aircraft. This module works on two frequency ranges, like that is on 970 megahertz and 1090 megahertz range. So this GRADSP, like in this is the block diagram which is GRC GNU radio flow graph which has been provided by the GRADSP repository itself. And here an USRP is made use in order to receive the signal from at 1090 megahertz or 1.09 gigahertz range. Then the received signal is sent on to a ADSB framer. Then the ADSB framer, the signal coming out from the ADSB framer has been passed on to the ADSB demodulator. Then again the signal from the ADSB demodulator is passed on to the ADSB decoder, which decoded the ES signals itself. ES like extended squitter signals or 1090 ES signals. And the decoded information can be either passed on to a TCP tunnel and also from the TCP tunnel to a web browser or like any other network route. So this is the flow graph, and the execution of the flow graph will give the like a decoded informations as illustrated here. In this figure, this is the response of the ADSP, GRADSP decoded. Here we have the message that is getting decoded. Here as you can see here, the type 5 indicates a short surveillance identification replay. This is a type 5 is the message which provides the aircraft identification details. So and it gives the identity of the aircraft that is flying. So then we have a type 4 message which gives the altitude information about the aircraft. So so as you can see here at type 4, it is showing that so short surveillance altitude replay from 742D. This is the flight information, flight data at 255 feet. So then we have type 0 message. Type 0 message is the air-to-air surveillance, which indicates that the aircraft is flying with certain speed, and this message is called as air surveillance. Then we'll be having a type 1 message, which indicates that the aircraft is on ground, and it is called as a ground surveillance message. Then we'll be having a type 2 message, which provides the information about the longitude of the direction, longitude of the aircraft. Then we will be having type 4. Again, it's a short surveillance altitude replay. Then we'll be having a type 5. Again, it's a short surveillance identification replay for the aircraft. So these are the ADSP message informations that gets decoded with the help of GRDSD. Now, like once we are done, and now we are done with the GRDSD, like OT module or the plugin for GNE radio. Now we'll check on like another open source tool for the USRP, such as software RFNOC, which stands for Radio Frequency Network on Chip. This RFNOC is a network distributed processing tool which enables FPGA processing for the USRP device. This RFNOC gives the flexibility, like in order to develop a custom-based FPGA accelerated digital signal processing task with the help of hardware description languages such as Verilog or VHDL. And it also gives the ability to create FPGA images with the help of GNE radio and decrease the processing time for the FPGA engineers by making use of the Xilinx IP into the USRP platform. Since the USRPs makes use of the Xilinx chipset, we can the IPs which are available on the Xilinx Vivodo or the Xilinx supported IPs can also be used for the USRP environment. We'll check on the architecture of RF NOC. When it comes to the architecture part, here we have two sections, like which one is the host based PC section and another is the USRP FPGA based section. On the host based PC section, like on the Linux operating system, a GNE radio is run as a host based software, and this GNE radio interacts with the USRP hardware with the USRP hardware driver. And RF NOC is built as a OOT module in GNE radio, such that the RF NOC blocks are available in GNE radio. Once we have the RF NOC blocks available in the GNE radio, this RF NOC RX underscore radio, RF NOC RX underscore streamer, like communicates directly with the help of communicates directly to the RF NOC radio block, which is present on the FPGA fabric. So the communication happens with the help of Ethernet connection or like a physical layer. From the physical layer, like on the FPGA fabric, there will be a network on chip core which controls the RF NOC blocks, and these RF NOC blocks are also called as computation engines. And the computation number of computation engines will be attached to the NOC core. And each of the NOC, RF NOC blocks will have a user defined functionalities. So then the communication we can see here the FFT block which is present here. This FFT block is a software based FFT block which is from the GNE radio. So if we want to make use of FPGA acceleration in order to implement this FFT block, we can go for the RF NOC development and make use of the Xilinx FFT IP core and create a custom based computation engine or the RF NOC block and attach it to the NOC core and have the FPGA accelerated FFT implementation. So we can, as we can see here, if we replace the FFT block with the RF NOC FFT transform FFT block, then we will have a direct communication with the RF NOC block, which is present on the FPGA fabric, so that the processing time will be much faster and we'll be having a parallel execution. And the signal processing task will be very much accelerated in this application, and the software FFT can be replaced with the help of the hardware based FFT using RF NOC. Once it is replaced, so the communication happens this way. The RF radio block will receive the samples, and the received samples will pass through the NOC core of the FPGA fabric to the another computation engine, in which the user based algorithm is realized, And this user-based algorithm, such as for example RFNO K50, performs performs its execution, and the response is passed on to the physical layer again back to the host software with the help of UHD USRP driver. So the communication between the RF blocks happens this way. Like the samples will be received with the help of an RX interface, and the received information bits will be passed on to a FIFO. From the FIFO memory, the information bits will be grouped into a set of packets with the help of a packetizer. Then these packets will again be depacketized and again be sent back to the depacketized, and can be passed and is sent to the NOC core, and again from the NOC core handles the exchange of packets from one block to another block, and from the NOC core, the packets gets pushed to the RFNO K50 block, and in the RFNO K50 block, the packets get depacketized with the help of a depacketizer, and this the again the information bits will be passed on to the FIFO memory, and the information from the FIFO memory again will be passed on to the Xilinx A50 IP, like which performs the like hardware based A50 implementation, and the output from the A50 IP goes back to the FIFO for the in order to pass it on to the host PC. Like the information will be grouped into a packets again, and will be passed on to the NOC core, and it will be pushed onto the host PC through UHD. This is another example in which RF block can be built, like using GNE radio. Here as a noise source is taken, and RF knock FIFO is made use. A FIFO block is made use, and the output of the FIFO block is passed on to the FIR RF knock FIR block, and the response is plotted onto the F50 block. So this is the response it looks like. The example one. Like when building the when we go for the RF development, like this is the GUI that is available. In order to have the RF development, we need to have UHD installed, and we need to have like a complete package of design package for Xilinx Vivado Design Edition, and here we can see the first section indicates the target FPGA, like some of the supported USRP is USRP X310 or N310 or N320. So like these are like these are the supported images. That and then we'll have the list of available blocks. Some of the blocks will be pre-built by ATES Research, and some of the OT blocks can be developed by the user itself. Then the blocks can be pushed on to the bit generation with the help of the arrows. Like the 5 indicates the block should be built, and 6 indicates the block should be removed from the build. And before going for the build, we can also have the FIFO to be built as well, and we can also open the Vivado GUI during the build process. And if we can also have the add a few more OT modules as possible, and it is also like gives the flexibility in order to import the flow graph from the GNE radio blocks also with the help of GNE radio companion. And once we go for bitstream generation, like this is an example build how the RFNOC images will be built. So like one such example, one such open source project which is developed for RFNOC is from Thesis Core. Like this Thesis Core is an open source community which makes use of RFNOC and has developed a 128 branch polyphase channelizer in order to have spectrum shaping requirements. So like this is one such example which we are tried, and this is how the FPGA build once the complete build has been happened. This is how the implementation details looks like on the FPGA. Then once the design has been implemented, then the bitstream will be generated, which can be used to program the FPGA of the USRP. Now we can check on another software, another open source software such as OpenBTS. This OpenBTS is a 2G emulation toolkit which implements a typical GSM architecture in a software. It basically includes all the components of the 2G generation digital cellular communication standard. Like it operates over 900 and 1000 megahertz band frequency band, and consists of four different parts that works together, such as a mobile device which works as a user equipment UE, a base station subsystem which works as a base station, a network switching subsystem, and a operation and support subsystem. The image here shows the typical architecture of a open BTS system. Here, in this architecture, the mobile, for example, a 2G cell phone or a 2G dongle gets connected to the open BTS. Gets connected to the open BTS, which is installed on a host PC which is running a Linux operating system. Using OpenBTS, the mobile can directly connect to the PSTN, which is the public switch telephone network, with the help of an internet connection. The OpenBTS connects to the internet with the help of SIP, which is the session initiation protocol, and RTP, real-time transport protocol. Once the 2G network is created, the signals are transmitted with the help of a USRP, and this USRP acts as a trans receiver system for the base station, and the like USRP will be transmitting, and the user equipment will be there. So these are the setups looks like. There will be a host-based PC, like which runs OpenBTS on a Linux operating system. Then there will be a USRP which gets connected through a high-speed interface to the host PC, and which acts as a trans receiver system. And this USRP connects to multiple base stations, multiple mobile stations. Sorry. So this is a simple demonstration, like how the OpenBTS is made. Yes.
Implementation of a GSM.
Sir, audio is audible, sir? Ma'am? Sir, audio is there, sir. Audio is audio. It's not coming, sir. Once again, so I'll change check for setting. Sir, it's audible, sir. Okay.
Yes, Murthy, like it was very low.
In this GS way, there we use of a USRP. A USRP is a multiple small block used for software design, and we use also a personal computer. The behavior of a GSM is yes. This is
Hello.
Ma'am. Yes, ma'am.
Actually, it's not coming out that clearly.
Okay, 1 second, ma'am. Ma'am, in the settings, there is no other option. Ma'am, now, ma'am.
Actually, it's not audible only.
Okay.
How about others? Like we'll check with other participants.
Audible, madam. He's audible.
Audible.
Ah.
No, he is audible. He is audible.
Ah.
But what record he is trying to play, that is not audible.
Let him play now. I will check once again. That's not audible.
That's what he is trying to do.
Okay.
Yes, sir. True, true, true.
in this video we illustrate the implementation of a GSM with based system with the use of a USRP. A USRP is
Yeah, it's better. It's
smaller
better.
part used and use
What, ma'am? Hello?
Yeah, it's better now.
It's better. Okay, ma'am. Thank you.
in this video we illustrate the
1 second, ma'am. I'll play from first.
In this video, we of a GS with the use of a USB. A USB motor board used for safety and we also the behavior of GS is achieved by using OpenVTS. This is a set access point which allows standard GS mobile phones to be used in voice and now we present the materials that have been used to implement OpenVTS. We're going to start by mentioning the USRP. In our case, USRP 2930 for national. We also need a computer to handle Linux Ubuntu 12.40 LTS. We also need software that communicates the computer with the USB. In our case, the USB drive. At last, two unknown phones that will be connected and will allow to pick the phone and send them. Okay, the software used to implement OpenVTS is a Google Nexus 4, running the latest version 4.2. Now we need to select the network that we're going to connect to. So it's basically have to go to set and look for the mode access control. It's recommended that you select only two networks when it's not entirely. So select network operator. And the first one is search for the network that are available. It's important to mention that this is only from basically we see the single mobile, AT&T, and then over the DS network which is main. So now we select it, automatically streaming to the network. Now we're going to demonstrate how to send and receive messages. It's important to mention that as soon as the phone is connected, you can assign a number to a specific phone. In this case, the number for this phone is 1, 2, 3, 4, 5, 6, 7, 8, 9. And for this phone is the reverse, basically start and ending in 0. So we're going to head and try to send a message to one of the as you can see, the other phone received the message and it displays the number when it received. We can try sending back a message. Can we hide? As you can see, we received it. So that's how we implement messages using over. Okay, now we're going to show how to make a phone call. So basically, as I mentioned before, we're going to dial 1, 2, 3, 4, 5, 6, 7, 8, 0, which is the number for this one. Now it's dialing. Well, here that is being connected. Okay, this video demonstration of how we implement VTS using the user. If we were able to show how to make phone calls, send messages using implemented network. Thank you.
Hello?